So hello again. This is Roger Kochbar for the Bioelectricity course. We're in week 8, our final week, and this is lecture segment number 9. Here in this segment, we're going to start talking about field stimulation. Field stimulation is what is mostly done most of the time. We talk about it here in a geometrically idealized way, but it's not too far from many real situations. For field stimulation, it's good to begin with an idea of where current is going. So let's just try to draw an intuitive mental picture of why field stimulation is having any effect on the fiber at all. After all, you could say, look, we have a long fiber within a big space. The electrode is outside of the fiber. The electrode is away from the fiber. So why should the electrode be making any difference at all to the voltages from the inside to the outside of our fiber? That's a very good question, but let's think about the current flow pattern. So here's our stimulus electrode. It's away from the fiber. We'll say it's minus I0. Once again, we will draw current flow lines going to our electrode. So here we just go to the electrode. That does not go in the fiber or out of the fiber. Doesn't affect the fiber. We'll draw another one going to the electrode. That one likewise. And here we draw another one, and that one likewise. But now let's draw a fourth. And for our fourth line, we'll imagine our current saying, it's getting crowded out here. There's a whole empty space over here inside this fiber. Let's just jump over this membrane and go on down here, and now we'll come back and go to the fiber this way. Well, now that one affects the fiber. That affects the voltage here, where the current crossed the membrane coming in, and that affects the fiber there, where the current crossed the membrane coming out. Of course, that's happening in both directions, so there's another current down here, jumping over the fiber, coming in, coming out, and going up to the electrode. And the extracellular ones as well, so there. It's absolutely true that most of the current, most of the time, is not affecting the fiber at all. But a little bit of it is, and it's that little bit that's having the effect. Right at the beginning of stimulation, one can establish a special rule called the activating function. The activating function depends on this quantity, the second derivative of phi e, with respect to the distance along the axis. In this equation, the axial direction is z. Let's think about how that works. Here's the electrode. It has a current. It creates voltages around it in the field. So here are the voltages. I'll draw lines of constant voltage. That's the highest. This is the next highest. This is the next highest. These are all spheres, just like that. Now what this term tells us to do is it says take the second spatial derivative of this potential field along the direction of the axis. So we have to take the derivative here. And as you can see, what the derivative is not so obvious, except that whatever it is, it probably has a big bump near the center where the potential rises to a peak before it starts dropping off. So we have this term, the second spatial derivative of the extracellular field. Do you remember that in analyzing the track, there was special meaning attached to the second spatial derivative of the intracellular potential, because the second spatial derivative in that case was the membrane current. Well, here, nothing is happening inside the fiber, at least not at the beginning. So the second spatial derivative in this term is again the membrane current. So because it's the membrane current, what happens is what you'd expect to happen, and that is this term, which this term is called the activating function, is proportional to dVm dt. The transmembrane potential changes right at the beginning in proportion to the second spatial derivative of the field that's established by the field stimulus electrode. Let me just say that again on a new slide because that's an important result. At the start of excitation, for a fiber that's at rest, just that very special case, but a very important case, this term, the rate of change of potential with time, that term is equal to, with the constants, this term, these Ri, Cm, times the activating function. Or said a little more loosely, at the beginning, the rate of change of potential with time goes as the second derivative of the extracellular potential around the fiber and in the direction of the fiber axis. This is a remarkable equation for another reason. Be sure to notice it. On the left-hand side, we have a derivative with respect to time. And on the right-hand side, we have a derivative with respect to distance. So this is one of those relatively few equations that we have where changes in time are related to changes in distance, rather than everything being in time or everything being in space. The activating function is the beginning. It's not the end. It's the beginning of what happens with the stimulus. To find out what happens at the end, we'll have to go on to our next segment. Well, I like these cacti here because activating functions are a little bit of a prickly topic. Ho, ho, ho. Thank you for watching, and I'll see you in the next segment.